Hello, welcome to the second video. In this video, we're going to talk primarily about what it means to be acidic, or strongly acidic versus weakly acidic, and what that pH means. When you hear pH equals something, what does that pH actually mean? Okay. So first of all, we know that acids will give hydrogen ion, which is really hydronium ion. Bases will give hydroxide, and water will react always at some level to form hydroxide ion and hydronium ion. And as you can see here in this image, the water is giving up one of its hydrogens. One of the hydrogens skips ship and goes to the other water molecule. And then you have one water molecule missing its proton and another water molecule that has that proton. We call them hydroxide and hydronium. There's always some of these floating around in water, although you can deionize water. You can pass water through a magnetic field and all the positives and negatives will move to the side and you get like 3 streams out the bottom, and the middle stream is completely deionized water. For some science experiments you have to do that. I used to always use deionized water in the biochemical experiments I did when I was a biochemist. That doesn't stay deionized for long, but if you use it right away, you have a pretty pure sample of water. So water will react with itself, and we call that self-ionization. It's a self-ionization reaction. And when it does that, you get a certain amount of hydrogen ion and a certain amount of hydroxide ion. For a neutral solution, those two things are equal. The H positive equals the OH negative. And that's what those little symbols with the why it's in brackets. Brackets means the concentration. And it turns out that in a neutral solution, what we call the ion product constant, hydrogen ion times the hydroxide ion, the product of these two things is a constant for water. And that constant happens to be 1 times 10 to the negative 14th. So if they're equal, that means that the concentration of hydrogen is 1 times 10 to the negative 17th, and the concentration of hydroxide is 1 times 10 to the negative 7. I think I said 17th, I mean 7. Because 1 times 10 to the negative 7th times 1 times 10 to the negative 7th is 1 times 10 to the negative 14th. These are very small numbers. These are moles per liter, very small numbers, 0.0000001. Right? So very small concentrations, but that's neutral water. But if that concentration shifts one way or the other to where you can get all the way up to 1 molar, so from 1 times 10 to the negative 7th molar to 1 molar hydrogen ion concentration, and you can see that there's a huge range of strength in acids. Now the thing is, this is a 10 to the power scale, right? So it's a huge range. So when hydrochloric acid dissociates in water, it produces hydrogen ion. But there's already some hydrogen ions in water at a very small amount. But if I add more hydrogen ions, that makes the solution more acidic. And if I take sodium hydroxide and I add more hydroxide ions, that makes it more alkaline or basic. So it's just the balance that's drawn. If I increase the OH, the H positive has to go down because some of this OH will react with the H positive to go back and form water. But I'll end up with an imbalance because the product of one times the other will always be 1 times 10 to the negative 14th. So if I increase one, the other one goes down. So if I have a hydrogen ion concentration greater than the neutral, which is 1 times 10 to the negative 7th, then I have an acid solution. And if it is less than 1 times 10 to the negative 7th, then I have a basic solution. But writing out concentrations this way is not really fun. We want an easy way of giving hydrogen ion concentration. So as I just said, increasing the concentration makes it more acidic. So for a neutral solution, H positive times OH negative, 1 times 10 to the negative 14th, as I said. But we'll use this thing called pH instead. So let me ask a question. How many free hydrogen ions are there in 1 liter of neutral water? Well, if it's neutral, it's 1 times 10 to the negative 7th, or whatever, these two have to be what, so whatever you can square, so the square root of 1 times 10 to the negative 14th, since these two are the same value when it is neutral. But this 1 times 10 to the negative 7th, we have an easier way of doing this, and we call it pH. Okay? But first, let me just drill home. When it's neutral, those two concentrations are equal, and they both equal 1 times 10 to the negative 7th. So let's look at some different numbers here before I move on to pH. Clearly, classify the following as acidic, basic, or neutral. So if I have a hydrogen ion concentration of 6 times 10 to the negative 7th, that is less than 1 times 10 to the negative 7th. A larger negative power means a smaller number. So this would be basic. Now, what if I gave you hydroxide ion concentration instead? And I said hydroxide was 3 times 10 to the negative 2. Well, this is a very big number compared to negative 7. So if the base has gone up, the acid has gone down, and this is basic. So just like if the H positive is greater than 1 times 10 to the negative 7th, it is acidic. If the hydroxide is greater than 1 times 10 to the negative 7th, it is basic. Here I have 2 times 10 to the negative 7th. 2 is bigger than 1, so even though this is only slightly acidic, it is still acidic. Hydroxide of 1 times 10 to the negative 7th, if hydroxide is 1 times 10 to the negative 7th, so is the acid, and this last one is neutral. So that's one way of doing acid-base strength. We look at the concentrations of hydronium or hydroxide. But another easier way is with this pH thing, where I'm going to head next. But first, make sure you understand hydrogen ion concentration and hydroxide ion concentrations. All right, but instead of the concentrations, we simplify with what we call a pH scale. This is a logarithmic scale that varies by powers of 10. And what pH equals, pH is equal to the negative log of the hydrogen ion concentration. So as we said, if I increase hydrogen ion concentration, it's acidic. The standard hydrogen ion concentration when it is neutral is 1 times 10 to the negative 7th. If this number gets bigger, and 1 times 10 to the negative 6 is bigger than negative 7, it is acidic. If it was 1 times 10 to the negative 8, that would be smaller, and it would be basic. And it's all because we have this reaction, which is highly favored on the water side, where you always have a little bit of these. And if I increase one of these, I can make it either acidic if I increase hydronium, or acidic if I increase hydroxide. Because the product of these two concentrations in water, the ion product constant, is 1 times 10 to the negative 14th, molarity squared. So if I do this negative log of the hydrogen ion concentration, and I'll do up here and then I'll go to the slides. The negative log of 1 times 10 to the negative 7th is, so the log of 1 times 10 to the negative 7th, if it's the log 10, 10 to the negative 7 power is 10 to the negative 7 power. So the log of 10 to the negative 7 is negative 7. So I take a negative of it and I get 7. So when it is neutral, I get the negative log of 1 times 10 to the negative 7th is 7. If it was negative log of 1 times 10 to the negative 6, I would get 6. And if this was 8, I get 8. Notice that if this number is a 1, if the first number is a 1, the pH just happens to equal whatever the exponent of that 10 is, because that's how log works. 10 to what power equals this? 10 to what power equals 10 to what power? The power is going to be the same. All right, so it's the negative log of that. So here's some more examples in the PowerPoint. If pH of 5 would be 1 times 10, would be the same thing as saying 1 times 10 to the negative 5th H positive. So if pH is the negative log of hydrogen ion concentration, if I have the hydrogen ion concentration, I can figure out what the pH is. By the same token, if I want to know the concentration of H positive, that will equal 10 to the pH power. So if I have a pH of 5, then the hydrogen ion concentration will be 1 times 10 to the, oh, and I need a negative there, 10 to the negative pH power. That's the same thing as 10 to the negative 5. 5 becomes 10 to the negative 5. So if H positive is 1 times 10 to the negative 3, then pH equals 3. It's acidic. If H positive equals 1 times 10 to the negative 12, then pH is equal to 12, and that's basic. So pH can tell you whether it's acidic or basic, and you get a scale that goes from 1 to 14, or really 0 to 14. So pH is equal to negative log of H positive. H positive times OH negative is 1 times 10 to the 4th. pH of 5 would mean 1 times 10 to the negative 5th hydrogen ion concentration, which is the same thing as saying 1 times 10 to the negative 9th hydroxide. Because I could take 1 times 10 to the negative 14th and divide it by 1 times 10 to the negative 5th, and I would get 1 times 10 to the negative 9th. When you divide exponents, you subtract, so negative 14 minus a negative 5 is negative 9. Likewise, if the hydroxide ion concentration is 1 times 10 to the negative 3, then the hydrogen ion concentration has to be 1 times 10 to the negative 11, which would be basic because that would be a pH of 11. If the pH is greater than 7, it is basic. If the hydrogen ion concentration is less than 1 times 10 to the negative 7, then it is basic. As the hydrogen ion concentration goes down, the pH goes up. That is one thing to keep in mind because it's a negative logarithmic function. And just like you have pH, you can also have POH. And if POH is the negative log of the hydroxide concentration and pH is the negative log of the hydrogen ion concentration, if I add these two together, they will equal 14. Because if I multiply the concentrations, I get 10 to the negative 14th. If I add the pH POH, I get just the 14, not the 10 to the negative part. So if you haven't had logs before, just try to keep in mind those basic tenets. And then you can always do the logs on your calculator. So we end up with this scale that goes from 10 to the 0 power all the way to 10 to the negative 14th power, and that's the hydrogen ion concentration. As the hydrogen ion concentration goes up, 10 to the 0 is the high value, that's acidic. As the pH goes down, and notice how it's just following this exponent, as it goes down, it gets acidic. POH is the opposite. POH is the concentration of hydroxide ion concentration. And just like pH, it goes from 10 to 10 to the negative 14th. If the POH is high, it's acidic. If the POH is low, it's basic. So they're just flipped from one another. So we have pH is equal to negative log of hydrogen ion concentration. H positive is 10 to the negative pH. Now a few things to keep in mind about pH and POH. Okay? Over here. I can have a pH of, let's say, 6.7. This, I do not say that this is equal to 1 times 10 to the negative 6.7. I can say that a pH of 6 is equal to 1 times 10 to the negative 6. And the reason for that is because we don't use decimals in our exponents. But if I was to put this into my calculator and hit enter, I don't have my calculator on me, so I don't know exactly what it would be. My calculator is going to give me some number, let's say like 1.8 times 10 to the negative 7. Your calculator will convert this into the proper value. It'll say like you might get 1.8 up arrow negative 7, which is the same thing as 1.8 times 10 to the negative 7. You might get 0.00000, where am I at? 1, 2, 3, 4, 5, 6, 7, 8. You might get this value, but it will convert this into a proper form. And the reason I say that is if I gave you a question on the test, what is pH 6.7 equal in hydrogen ion concentration? This would be the answer on the test in the multiple choice, not 10 to the negative 6.7. Okay? But if I give you a concentration, let's say that I tell you that the concentration is 1.8 times 10 to the negative 7, and I want you to give me the pH, what you would do in that case is you would do the negative on your calculator, or you can just leave the negative out and put it on at the end, and say log, and then you want to put all of this in parentheses, because if you don't put this in parentheses, your calculator will do log of 1.8, find that answer, and then multiply it by 10 to the negative 7th. It'll move this answer, it'll move the decimal 7 places of this answer. But you don't want to do that. You want to make 1.8 into 0.00000018, and then take the log of this. So you want the log of this to get the pH. So when you do these calculations on your calculator, make sure that you put the entire hydrogen ion concentrations in parentheses so that you'll get the right answer. pH is the negative log of the hydrogen ion concentration. If I want to go the other way, H positive is equal to 10 to the negative pH power. And you may likewise, if I told you that the pH was 6.7, you would put into your calculator 10, and then you would do exponent, whatever your exponent function is on your calculator, negative 6.7, and then equals or execute or whatever, and then that will tell you whatever it is. Now I just made up this 1.8 value. I don't know if that's what it is, but you want to, so it's 10 to the negative pH value is how you go from pH to hydrogen ion concentration. So this is hydrogen ion concentration. pH to hydrogen ion concentration, 10 to the negative pH. Hydrogen ion concentration to pH, negative log of the hydrogen ion concentration in parentheses gives you the pH. If the pH is less than 7, it's acidic. If the pH is greater than 7, it's basic. If the pH equals 7, it's neutral. Now, another way that we measure pH, at least not to an exact value like we can with the pH meter, but one way that we measure pH is with indicators. And your book gives a whole lot of different indicators. A common one is phenolphthalein because it turns clear when it's acidic and pink when it's basic. This really small image, I apologize, but there are many different indicators. When we do a titration lab, we're actually going to use bromthymol blue, which is yellow when acidic, blue when basic, and green. And it's green only through a very small range. So if you want to know if something is neutral, you put a little bromthymol blue in it, and if it turns green, this kind of lime green color, it is neutral. So it's a really good neutral indicator. You can use other indicators like orange for acidic. There are lots of indicators out there. You can even use, in a lab I used to do, we used to use red cabbage as our pH indicator because red cabbage has a huge pH range. I might even have an image of that. I guess I don't. You look online about using red cabbage as a pH indicator. I'm going to add that. I'm going to add a note so that I look a video of that up so I can make sure I put that online. So we're going to do red cabbage as a supplementary video and strong acids. I already know strong acids, but I'll make a note just so I remember to put that down as a supplementary video. All right, that's it for this video, and probably be able to finish up in one more video, which our next video we will cover acid-base theories. So we're going to go back to other ways to look at acids and bases.